Our next invited speaker is Urvashi Rau from National Radio Astronomy Observatory, and she will speak about uncertainty quantification in radio interferometric imaging.
Hello, everyone. Thank you for joining in today. This talk's going to be about defining correctness of scientific software and how this generally plays out in the field of astronomy, and in particular radio interferometry. So let's start with a picture. This has been taken from the book referenced at the bottom. It shows what scientific software generally is. There is the real world, and then you have to make a bunch of simplifying assumptions and approximations to form a mathematical model of that world, which is then encoded with a variety of discretization and algorithm choices into a computational model, which is then implemented on computer hardware using software. Okay. So at every stage, there are assumptions and choices being made which deviate from the real world. And that's what contributes to what we call accuracy or error. Now, of course, in astronomy, we are making images of unknown structures. And so there is no known absolute truth in general. And we are using instruments whose characteristics must be modeled and corrected for in the software. In real life, what this translates to is questions about what defines the absolute correctness of an end result, how much can we trust it, then what defines the operational readiness of the software, because given the understanding that there are going to be differences and errors, how good is good enough? And finally, as software and code evolves, what does one do when numbers change? What can you trust and what can you not? So there are a number of standard development practices, and all of them talk about requirements, specifications, and tests. And at the core of writing a test or a requirement are these two things. You have to have a truth value that's known and understood and accepted. And you have to pick a tolerance which can encompass any of these different criteria against which you can compare your output values. Okay, so let me say a little bit more about truth values and tolerances. Truth values, in our case, where we are observing something unknown, can come from simulations, where in this case, it means making a model of what you think the sky is and simulating a controlled environment and producing a data set that you then take through your standard data reduction process. So a simulation essentially lives in this mathematical model space, and it tests the rest of the system. Now, you can always also use a test observation, which of course is much more realistic. It comes from the real world. But the caveat is that you're not going to have a knowledge of absolute truth. You could use an independent measurement from some other telescope when available. But in reality, it turns out that what one uses is just the value obtained whenever the test was written as the practical approximation of what truth is, given a human evaluation proving that it's good enough. So these are about truth values. What about tolerances? There are a lot of options to pick. You could pick an accuracy needed for the astrophysics, which is a real-world metric. For example, what is the error bar that I can tolerate on a certain measurable so that you can distinguish between two different theories, for example. You could also pick an accuracy defined by the instrument's limits, which is the best case scenario for a given instrument and observation. Usually the astrophysics limits and the instrument limits are defined beforehand in conjunction with each other, but sometimes they can be different. You could also pick the accuracy of the algorithms and implementations themselves, which means leaving out the real world and just quantifying how good that, given your mathematical model, how good does the rest of your system compare, assuming that your mathematical model is real truth. So that's what that metric is. You have to factor in where machine precision comes into play, and when it makes sense to use machine precision levels as your threshold and when it does not. And of course, all of this has to account for the effects of error propagation. So given so many options, the practical reality that comes to play is that when code and algorithms evolve, your numbers are going to change. And you're going to end up with questions of what changes are okay and what are not. which kind of tolerance to use. Sometimes your best result truth values can change as your algorithms improve. And sometimes you have a bug which mimics the effect of a legitimate real world to model approximation. Now, obviously, if there's a bug, it must be fixed. But in some cases, if it's not really a bug, but it's a difference due to legitimate choices that you have to make when converting a real world model into a computational, reality, you can end up in a situation where you reach the point of diminishing returns, and you have to start asking the cost benefit question of when is it worth it and when does it matter. So all of this comes into play in real life. So let's get into a bit of a case study. I want to describe radio interferometry and how all of the sources of uncertainty play out there, and how the Casa software package attempts to navigate the situation. So radio interferometry, for people who do not directly work in it, is an indirect imaging technique. This means that we do not make images of the sky brightness directly, but we make measurements of the two-dimensional spatial Fourier transform of the sky brightness. It's an incomplete sampling. We assume that a measurement noise is Gaussian random. And our reconstruction process is an inference problem. It's an iterative numerical optimization, and it solves for, in different stages, parameters of both the instrument and the sky model. So in pictures, it looks something like this. You have a set of antennas and receivers, and signals taken from all of them are correlated, and there's a set of signal processing with their own quantization and assumptions in there. The data set that comes out of this goes into an archive and is then taken for post-processing. Now, post-processing is where we're going to focus our attention today. And there are three main steps of post-processing. The first is what we call flagging, which is essentially just identifying and masking out corrupted data. So there are a couple of ways in which flagging affects the error budget. The first, of course, is data loss. Since you are identifying and throwing away some data, the amount of data you discard is going to affect the best possible outcome from that data set and the theoretical noise limits and such. Flagging also involves outlier detector algorithms, and so you now have to contend with the accuracy of those algorithms. The next step is generally calibration, where you have to solve for and apply corrections for instrumental effects. Okay. And here also now, this is an iterative solver, and there's a model of your instrument that is approximate. And so you have to account for the discrepancies between that model and real life. And of course, the available signal to noise to allow you to even get a robust solution. The third step is image reconstruction, which is again, iterative model fitting while correcting for some other instrumental effects. And so here too, you have to contend with various approximations in the models being used, the uncertainty of the reconstruction process itself, since we are do an inference problem because of incomplete sampling, and also the fact that there needs to be enough signal to noise to get a robust solution. So all of these contribute to errors. Now, an actual data reduction sequence is not just 3 steps. It looks more complicated, where there are usually a variety of flavors of each step interspersed within each other. And for example, this picture here shows what one of the instrument pipelines implements. It's a whole sequence of steps. There are feedback loops, conditionals, and all kinds of heuristics implemented in it as well. And so if you're looking at the output from a pipeline like this, you now have to also deal with the accuracy of the heuristics that have been developed on some data sets and applied to others, and the effects of error propagation. So putting this all together into our favorite picture again, you have the real world. In this case, it's just the physics of the incomplete sampling of the data domain. You have the instrument system noise and the amount of data that you can keep or lose. You have all of the models that you put in, which are the simplifying assumptions. For example, you model the sky distribution with a bunch of delta functions or wavelets, which is an approximation. You model instrument parameters differently, and you make an assumption that your noise is perfectly Gaussian. When you're implementing an algorithm, the discretization comes in. And for example, it's how do you control aliasing errors? Or what are the pixel or bin sizes you choose for various things? And of course, the algorithms themselves and how much you allow control for them. You then have to run this on different kinds of hardware, because hopefully your software is going to outlive system libraries, and you're going to have to keep updating things and changing parallelization approaches as your requirements change. And so you're going to start to see differences simply because of this part of the problem. There are, of course, going to be bugs, and you have to contend with the effects of error propagation. Okay, so this is how this is an example of how all these factors play together in, say, radio interferometric imaging. So how do we deal with this? First of all, what is Casa? Casa stands for Common Astronomy Software Applications. We are a general purpose suite of radio interferometry analysis tools operable within a Python environment. And we put out 1 to 3 releases per year. We are a team of about 20 people, a mix of software engineers, algorithm scientists, and astronomers. Our stakeholders are mainly the VLA and the ALMA telescopes, although people from other telescopes also use our software. In recent years, there have been pipelines developed on top of Casa for the VLA and the ALMA telescopes, and they are some of our dominant stakeholders. And more recently, the NGVLA telescope, which is hopefully going to appear in the next decade, it has also begun using our code for some of their tests. We partner with an algorithm R&D group, a pipeline development team, and several other associated teams for parts of the development. And I should stress that the production pipelines, which a lot of people hear about with these telescopes, are built using Casa methods with heuristics by a completely different team. What we are talking about today is just the building of the library and the tools which are used by these science application teams, so to speak. You can get a feel for the size of our user base from this plot of the number of unique monthly users of the software obtained by telemetry measurements. We follow a pretty standard development process involving requirements, specifications, verification, and validation. And the parts in the red box here are what the core team is responsible for, and we interact with the science application folks on either side of the process. So where does numerical accuracy come into all of this, and how does this play out for us? To get there, let's talk about the operational complexity that we work with. We support a variety of usage modes. There's manual data reduction, where people interactively use the software. This is where people are exploring how best to reduce their data. So the emphasis is on flexibility, with a lot of parameters and options to tune and explore the algorithms. And this is also where a lot of new options and features are always being added. So the code is in flux and the code is changing. We also have production pipelines that we support from the same code base for multiple telescopes, and they have slightly different needs and requirements, but they all require stability and reproducibility of the results. They do sometimes require algorithmic evolution as the pipelines introduce support for new modes, but they also have a very, very low tolerance for unasked for changes. We also have to support algorithm R&D, which is more of a software design aspect and less of an operational one. It's about modularity mainly. But this is the range of use cases, usage modes that we support. We have to operate on a variety of platforms ranging from desktops and laptops to cloud operations, and different types of parallelization schemes. Our code base is predominantly C++ and Python for now, and we are experimenting towards moving to a more Python-centric ecosystem. Requirements are usually written as feature requests, algorithms, or problems to solve. And metrics are not often defined upfront. They're usually based on the best possible outcome after experimenting with the solution. And so often metrics and tolerances are defined post facto, not at the beginning. Sometimes independent analyses are available to do so at the beginning, but they're not always possible. And we have to contend with and live with that reality. So if you put all of this together, there's a lot of complexity with somewhat competing requirements. For example, you need to be able to constantly add features to the code and provide flexibility and tunability, which means more options for bugs as well. And you also have to be extremely stable for production pipelines. You have to evolve as the systems and architectures and operating systems change underneath you. And the numerical changes that come just because of this sometimes also get us into trouble because of the low tolerance for unasked for changes. The fact that metrics aren't always defined upfront, because sometimes they're just not, it's not just not possible. Your truth values keep changing based on your current output from the software. And so when the software changes, all of that has to be re-evaluated again. And so in the end, all this put together, people have generally become extremely wary of change. There is a certain degree of loss of objectivity in evaluating when things are acceptable for operations or correct or not. And this all leads back to a very inefficient development process. And so we are actively working on various ways to build trust so that we can improve the situation and make it more productive. So one obvious way to build trust is tests. And so we're increasing the test suite. We have a variety of tests, test types. There are what we call functional verification tests, which are the basic tests written against feature specifications, and the emphasis being code coverage. And they usually use small and simple simulations of data sets and test the basic features. So this is essentially testing the right-hand side and looking for regression and whatnot. You then have algorithm characterization, where we, on certain topics, go into much more detailed simulations and analyses using science metrics, and often compared with independently calculated metrics. If you have simulations, you have truth values to compare with. This essentially tests these the bottom and the right side of this diagram, which is assuming your mathematical model is a true representation of reality, how good are your algorithms and all of your implementation choices for solving that situation? That's what this tests. Then we have more real-world tests, which we call stakeholder verification tests, where for major usage modes, we have actual real data sets. And in this case, we use analyses, steps, and metrics relevant to the different stakeholders. And this is the place where we also track differences and changes at numerical precision level, which gets interesting sometimes. There are also pipeline validation tests, which I should emphasize are not run by us. They're run by the science application groups. And they test end-to-end analysis runs. And that's where the error propagation tests come in, metrics come in. There are also performance tests. And of course, there are also manual tests where people just use their own experience and technical expertise to judge whether something is correct or not. So all of this has definitely helped in improving the trust in the software. But there is still a large variety in the metrics, tolerances, and general acceptance rules. And we often run ourselves into loops trying to navigate this with a whole range of stakeholders with differing interests. So one of the things we're trying on this front is to try to go towards something consistent in terms of metrics as well. So again, this is not unique. These are some of these are pretty standard in other areas. We are hoping to at least pick some major usage modes for different telescope operations and get science-driven accuracy limits defined upfront. They could be in the form of requirements versus goals, where requirement is whatever is good enough for most operations, and a goal is what's the best case scenario. And this is also the algorithm development target. Along with this, we have to also demonstrate the numerical and absolute limits of the software given ideal data. And this is where the accuracy of the solution for an idealized mathematical model, how good is that? And that's what we may call a Z over here. And for this, we may use simulations or carefully designed test observations with definitions compared with results compared to known truth values. And now for a given use case or a usage mode, once you have these three numbers, in principle, it is possible to define clear acceptance rules. If, of course, your documented spec of the software is tighter than what's required for both the requirement and goals for the science, and this is clearly above the numerical precision level of your machines, then all is well. If, however, what your software can demonstrate is larger than, the errors are larger than what you need for any science, of course, that's unacceptable, and it needs algorithm R&D or a reevaluation of the requirements. The gray zone is the more interesting, where if what your software can do is good enough for most operations, but not good enough for everything. So it's acceptable, that means you can operate, you need not block operations, but improvements are obviously desired. And this is the gray zone where one gets into the state where you need to now track changes and understand every little change. Even though it may still be acceptable, you still need to know why the change happened, and things get interesting. and have to be done on a case-by-case basis, but there may not be a way to get out of this. And the goal here is to at least constrain this extra effort of detailed bug tracking and analysis to be only for the situations where it really matters and not for everything. The other side effect of this is when numbers change, what do you do? The hope is that we can use the tighter constraint, tighter of Y or Z, which is the best case for this use case, or what is the best case by the software. Pick the tighter of the two, and maybe use that as the tolerance for acceptance when numbers change due to unrelated reasons. I mean, by unrelated, I mean you change an operating system or change a compiler and the numbers change slightly. It's those kind of things. And basically to allow the code to evolve within these limits. Now, of course, there are pros and cons to this, and you might have slight bugs which cause differences only below this threshold. And yes, some of them may live on, but there is a compromise to be made. So this is what we are trying. We haven't fully implemented this yet, but we are trying this out for a couple of ongoing development topics to see how it goes. So going forward, for current operations and support of the ALMA and VLA telescopes and the various surveys and pipelines, we have to continue as is. And we will be working to define metrics retrospectively and try to evolve the way people view the correctness of the software. For a new telescope, that is the NGVLA, and upgrades to existing telescopes such as those planned for ALMA, we are most likely going to require a new software package, and work has begun on prototyping this. But here's an opportunity to define all of this correctly upfront. And so since we haven't started yet, we can theorize. And so let's assume that we can define clear use cases, metrics, and get acceptance rules decided upfront. From experience, we know that it is not enough to just do this once. And so the model has to also allow for evolution. And this situation is not different from any of the other new telescopes being developed by others in this field. But so we also have to do the same thing. At the same time, we are also evaluating what we're calling the Casa Next Generation Infrastructure project. And this is a move towards more open source third-party infrastructure to give us more operational flexibility, and even for some numerics. What this means in the context of numerical correctness is we might end up with reduced in-house control of numerics, which makes it even more important for us to get these use cases, metrics, and acceptance rules sorted out at the start. Otherwise, this is not going to get off the ground. So we'll see how it goes, but that's basically how our project is trying to deal with and navigate this situation. Okay, so that's all I have. I'd like to end by perhaps inviting some discussion. If there are other telescopes and projects who have successfully navigated this whole issue, not just at the start when an instrument and a piece of software is new, but also as the system requirements and an instrument evolves. If you have tips and tricks, please do consider sharing them with the community and us. And for everyone else who has perhaps not gotten a chance to think about this entire scope so far in this level of detail, I hope that this has provided some food for thought. Thank you very much for your time.
Yeah, thank you very much. And I'm sorry I made a mistake in your title. I just had a brain fade as I was introducing you. I see you've already answered the question on Discord, and we have more questions coming in. Peter is asking, in Casa, are all steps basically MC-able? In the sense of Monte Carlo, I guess?
Yeah. I guess yes and no. I mean, you can run them, they're parameterized, but it may not be advisable to do so from a runtime point of view. The information that you would need to retrieve back is probably not going to be consistent enough. But from a point of view of just methods that you can run with parameters, yes. I hope that vague answer was okay.
Okay, and we have questions in the audience here. I see there's Space going to ask a question if he wants to ask it live. Landman will ask a question live. Just a second, he's coming to the microphone.
Hi, Urvashi. Thanks for the very nice talk. What I want to know, so in the development of the potential NG Casa, are you planning to move to a more modular structure? So if I only wanted to use some tools in Casa, but didn't want the entire, say, half a gigabyte of binaries, would this be possible?
Yes. In fact, we are even evolving current Casa to be more usable in that way. And in fact, some of the later releases have separated out what we call tools and tasks and different things separately. But going forward, we're looking at even separating things out even more into functional blocks that you should be able to call. So short answer, yes.
Okay. And just one more question, if Oleg allows me. Sure. Also, like in terms of developing these metrics and I suppose an implementation eventually, will that be housed in Casa or will it be a standalone project that can be accessed outside of Casa?
I don't have an answer for that. Right now, we are just trying to get it going within Casa. But the concepts of how you define these things have to be done along with the science teams. So we expect to have a set of documents, which will live documents, which will always maintain the current state of what are the use cases being supported and what are the metrics that are being used, and also how well are we satisfying those metrics or not. So some live summary of that we will hope to always have once we have this in place. And that hopefully will be accessible to the external community as well. I mean, this can be made public. So one example of this that we're trying right now is just for a specific case, is as simple as just making a Jupyter notebook that you can take from the Casa documentation as an example, run it on Colab, and have an example of what the code can do along with metrics and outputs. So we are putting together such things. That's an example for one feature. How we do this for everything, we haven't gone through the details of that yet, but I think your point is when there's information about the accuracy that is documented and how it fits, is that going to be publicly available? And I would hope so.
Okay, cool. Thank you.
Thank you. And we have a question from Landman now, live.
Hi, Urvashi. Thanks for an excellent talk. I'm happy to see that other people are thinking about these things as well. And I'm sorry if I missed this. Maybe I drifted a little bit. But when you define your quality control metrics, how do you actually do this without uncertainty estimates? Because as you say, it can come from a number of sources. Like incomplete UV coverage contributes to, you won't be able to reconstruct your model perfectly because of just that. On top of that, you've got noise. On top of that, you've got calibration errors. So if you don't have uncertainty estimates, how do you come up with quality control metrics and how do you sort of enforce them?
That is exactly the question that we are also trying to figure out. But you can separate them into two parts. So there are some parts which you can calculate. For example, if you know the noise thing. So if you know your input noise, number of data points, and how you're stitching together mosaics and things, you can predict noise levels and compare against them. The reconstruction uncertainty is the nonlinear part, and that you pretty much cannot with current algorithms. So there you go by empirical estimates. And so you either go by experience. So you say, okay, for all VLA data at L-band, empirically, the best accuracy we've ever gotten or seen on spectral index is 0.1. If I pull a number out of a hat like that, based on experience, you then set that number. But a more rigorous analysis is going to be dependent on the data set. And so it's hard to make a generic number. So that is going to be difficult. There's no easy way around that. The best thing I think we can say is, for the parts where you can predictably calculate, like noise and number of data points kind of thing, one should definitely do that. Use experience and model your experience as a metric and put numbers from empirical numbers for the parts that you can't directly calculate. And at least you have these two numbers in hand now, and then weight them appropriately and work with that. At least that's a theory. Let's see. Do you guys have any better ideas or solutions on this front, since you've also been thinking about it?
We have some, but none of them are implementable in Hubble time.
Yes, exactly. Monte Carlo ways are, of course, you can test for everything. But, yeah.
Thank you.
Great, thanks very much. We've got some more interesting questions in chat, but we're now out of time, so I suggest we take the discussion to the talk channel. Let's
Okay,
thank our
thank you,
speaker
everyone.
again.